Okay, welcome to page 2 of Guidesheet number 3. We're looking at projectiles at an angle. Now, in the previous video, we looked at filling out a table of velocities and accelerations for an object moving that's been shot at an angle. Here, we're going to fill out a diagram. It says pretty much exactly the same concept. Again, the acceleration in the x direction is 0. Therefore, Vx, the velocity in the x direction at any point in time, will be equal to the initial velocity, which in this case is 8 meters per second. So at every spot, the velocity in the x direction, be careful they switch locations here, 8 meters per second. So in the horizontal, the velocity is constant, no change to the velocity's value or direction. Now, in the y direction, just like before, our acceleration is that due to gravity. So the acceleration g is down at 9.8 meters per second squared. So we'll start at 29.4 meters per second. Now, 9.8 meters per second is a better way to think of it than meters per second squared. It means that we're, in this case, going to take away 9.8 meters per second for every second that it travels. Since each of these pictures is taken at each consecutive second, by the time it reaches here, it will be at 19.6 meters per second in the vertical. 29.4 minus 9.8. By the time it reaches here, it will lose another second, so it's going to lose another 9.8. It'll be down to 9.8. Notice there's no Vy here at the top. At the top, the velocity in the y equals 0. That's now how you know that you've reached the top of the object's flight, the peak flight point. Now, on the way down, again, the object doesn't hover there. The g is still 9.8 meters per second. It's not 0. The velocity in the vertical is 0. Because gravity keeps pulling, the object will start to speed up, but downward. And it will gain in the first second 9.8 meters per second. Then in the next second, it'll gain another 9.8, so we'll be up to 19.6 meters per second. Then it'll gain another 9.8, and we'll be up to 29.4 meters per second. As I mentioned before, this is a parabola, so notice the symmetry. 29.4, 29.4. Now, it's in the opposite direction, but the magnitude is the same. 19.6, 19.6. Opposite direction, same magnitude. 9.8, 9.8. Opposite direction, same magnitude. So don't forget to use symmetry in these cases. Symmetry is your friend. Okay, using that data, we're going to figure out the displacement, how far the ball has moved. Now, keep in mind, the displacement is going to be a vector. It's a straight line from where the ball started to where the ball finishes. So it's this straight line displacement right here that I want to measure. That means really what I want to measure is Sx, the distance in the x direction. Sx is equal to ux times t. We know the time because each second is a picture, so 1, 2, 3, 4, 5, 6 seconds. We're traveling at 8 meters per second, so we're going to be moving at 8 meters per second times 6 seconds equals 48 meters for the displacement. Now, it is a displacement, so it's also, the angle is 0 degrees. Height above the ground at its peak. Okay, well, that's going to be Sy, and that's Uyt plus 1/2 gt squared. Now, we're moving upward at 29.4 meters per second. Now, the question is, when does it reach its peak? Well, here in the diagram, it should be pretty simple. We just have to count the number of pictures. So this is time 0, time equals 1, time equals 2, time equals 3. So it's 3 seconds. Notice that's also 1/2 of the total time. Again, symmetrical. We're going to reach the peak at the halfway point. Plus 1/2 of g. Now you got to keep in mind that if you say this is positive, we're moving up is positive, then g, since it's pointed down toward the ground, has to be negative, 9.8 meters second minus 2. And that's also measured, multiplied by 3, but it's 3 seconds squared. Don't forget the squared. So this is going to be a positive number, there's going to be a negative number. We add them together, and we're going to get the height of maximum height at the top of the flight is 44 meters. And finally, the final speed of the ball upon hitting the ground. So we know that the horizontal velocity is going to stay 8 meters per second. We know that the vertical velocity is going to be 29.4 meters per second. Okay, now we want the speed. I really only need the value. I don't need the direction of this, but I do need to add the two vectors together. And they are vectors, so it's not 8 plus 29.4. It's 8 squared plus 29.4 squared. Take the square root, and we'll get the overall speed. So the overall speed is equal to 30.5 meters per second. Now, if the question had been what's the overall velocity, I would also need to determine the direction that it's moving as it reaches that bottom point. But for speed, it's just 30.5 meters per second. Now, in number 6, the only thing we're going to change is the ux. We're going to move at a different velocity. We're going to move faster. Okay, so if we move faster, the only impact of ux is it has nothing to do with the time to fall. It has nothing to do with the height that we reach. The only difference that u of x makes is the range. Okay, so sx is going to be greater. The distance that we travel on x is ux times t, but the time of flight has not changed, so it's still going to be 6 seconds, but we need to multiply it by 13 meters per second. That's going to make it go farther, 78 meters, but it doesn't take more time to reach that point. It simply goes further because it's moving faster in the horizontal direction. The overall displacement of the ball, Sx, is 78 meters. The time of flight is still the same at 6 seconds. The height above the ground, Sy, does not change. It's still 44 meters. If you put the values in, I didn't change anything about the y direction of the flight. I only changed the x direction of the flight. Now, the overall speed upon hitting the ground is going to be somewhat increased because now we're going to add together 13 meters per second to the 29.4 meters per second. And again, they're vectors, so it's a squared plus b squared equals c squared. Your final velocity upon reaching the ground would be 32.1 meters per second. Now, keep in mind, that's the velocity just before the projectile makes contact with the ground. Once we have another force, like hitting the ground, the object is no longer a projectile. So don't say that the final velocity is 0. The final velocity for the projectile is not 0. The total final velocity of the object may be 0, but as soon as it hits the ground, it no longer is considered a projectile. Okay, so that's another look at how we can track the motion of projectiles that are launched at an angle. We'll look at a couple of more things as we move on with the rest of the Guidesheet.